All right, so here are some basic packages, and I have already downloaded. Sorry, I should have told you that I have downloaded some files. Uh, the website is slow, so although this is only 45 megabytes, uh, it'll take too long for you guys to download it. So let me just try to read this into Python and show you what this data is like, okay? So first of all, when you have a bunch of files that you want to read in one directory, often it's better to use glob. It's more convenient to use glob. So let me copy the directory. I'm going to do from glob import glob. Now the OS has a different way of achieving the same thing, but I can never remember how to use the OS to do that. I always just use glob. It's easier. So the image files that I downloaded are in PGM format. Sorry. So if I do this, then and then see what this is. Oh, sorry. I need to grab all the PGM files. Okay. And then if I look, see all the files are there. And we can also look at the length of the PGM files to see how many images there are. Okay, so 13,233. So let me quickly explain what this data set is. You can search Google LFW crop _ gray to find this data set. You can download it. It's about 45 megabytes. And LFW is I forgot what L is, but faces in the wild. Yeah, that's so. Let me see. LFW faces in the wild. Labeled faces in the wild. Okay, so that's what it is. If you go here, you'll be able to get the color version. But where am I? Yeah. What this crop gray is doing is people realize that the original LFW data set has background where it kind of makes the recognition of the faces harder. So somebody took the LFW data set and just deleted all the backgrounds. That must have been a lot of work because there's like 13,000 pictures. And they also cropped it and made it gray. So let's load up this. To load up, you need the pillow. So from pillow, Python image something. Python image library. That's what PIL is. People call it pillow. Right? Import image. That's what we were using to import images. Right? Read images. Right? So and then we'll make a blank list and then go through all the file names in PGM files. And we're going to append faces.append np.array of the image.open of f. So here's what's happening. Image.openf reads all the file names, and then if you just read it the thing that you get is an image object, so it's not a bunch of arrays, but we want a bunch of arrays for us to put into the PCA. So that's why I'm changing it to a NumPy array, and after making it into a NumPy array, I'm appending it to the faces. Okay, and then just to make the later conversion easier, we're going to rewrite faces as NumPy arrays. Okay, so I'm going to make, so I'm first making a list of images, and then I'm making it into NumPy array. What happened here? PGM, oh, F in. Okay, so it's reading all the files. It's taking longer than I thought. Okay, so it's read. All right, so let's see what this is. plt.imshow. Let's try to look at faces number 9355. Okay, who's this? Huh? Muhammad Ali, right, you're right. So to figure out who this is, you can also print the file name. Print PGM files 9355. And if you look at the file name, it says Muhammad Ali 003. Okay, so that's what it is. And you can change this to get other people. So if I go through this, there are a bunch of names, mostly politicians. There's Andrew Agassi. Okay, the problem is I don't know the number for Andrew Agassi, so you can search up by going through everything. Let's see where Agassi is, right? So for I and F in enumerate PGM files. So if you enumerate, then it goes through all the PGM files one by one, but it also counts the number starting at 0. So not only I know the file name itself, but I know what number it is. So if is it Agassi Agassi in F, then print I. Let's do that. All right, so I have all these. 584. Let's just pick one and try to. 584. 584. Yeah, that's Andrew Agassi. There's a tennis ball blocking the view. Well, anyways, that's it. Right. Okay, so with this, what do we want to do? We already imported PCA from sklearn. So let's have our, I don't need this, so I'll just write over it. Let's say PCA, let's say PCA is equal to PCA with number of components. The bigger the number is, it will take longer, I think. I'll just do 500. Now I'll do 1000. Okay. And then we are going to fit our faces. So we're going to take all the pictures, all 13,000 people, and do a PCA transform. But the problem is our data is 64 by 64. PCA doesn't know how to handle that, so we have to flatten it. So we're going to reshape it as -1, 64 times 64. Okay, so let's see if I do that. How long is it going to take? Yeah, it's 1000, so it's taking a while. Maybe I should have done 200. Well, while it's running, let me just type in the next one, plt.imshow. Once the PCA computation is finished, I can look at the PCA components. Oh, it's done. Okay. What is PCA? Can someone explain? Yeah.
It's a dimensionality reduction technique
Okay.
used to reduce the amount of features that
Right.
that you would have. So let's say you have 20 features. You'd want to perform a linear transformation from R20.
Okay, good. Let me take over. Okay, so it's a dimensionality reduction. So what it does is it takes the most prevalent features. So the principal component 0, PCA 0, would be the most prevalent feature, which is another way to say it is like this is the feature that distinguishes the data set the most. So in the other YouTube video that I made, I tried to explain how just looking at the PCA 0 and 1 distinguishes your data the best, so that that allows you to figure out one image from the next. So you can distinguish one image from the next by using these PCA directions. Of course, you can't just do one direction. That would be impossible. So you might need something like 20 features, 100 features. So that's what it is. But another fact of the principal component analysis is that these features form an orthonormal set. And what that means is that if you take any data set like this one and you project into, say, the first 100 features and find their components, you can add them back again to reconstruct the data to pretty good reconstruction. Okay, so I just wanted to show you that. So let's see. The vectors are right now in the 64 by 60. It's one-dimensional vector, so we need to put it back to two-dimensional. Let's see how it looks like. So that's the first feature. Okay, that looks like what? What does it look like? Looks like a person's face, right? Yeah. Yeah. This is called an eigenface, and the reason being is if you look at the PCA algorithm, what it does is it takes the entire data set, treats like a matrix, and it does the singular value decomposition. But then what is singular value decomposition? It's basically taking the multiplication of the matrix by its transpose. It gives you a square matrix, which you can diagonalize by eigenvectors. So that means this face right here is actually some kind of an eigenvector of a matrix. The matrix size is huge. 64 times 64, that's 4096. Okay, so this is a vector size of 4096. 4096 numbers. That's what this is. Okay, so this is one eigenvector. Let's look at the next component. This is the next one. Okay. And then the next one is some ghostly images here. Let's look at something like 100. Let's see what that is. Okay. So basically these feature vectors, component vectors, try to pick up various features in the face. So if you project, it will give you how much of this component lives in there. Okay. So for example, if I take Mohammed Ali's face, which was 9355. Okay, so so let's say Mohammed Ali MA is equal to faces 9355. Okay, and let's say MA or just coefficients of the Mohammed Ali would be PCA dot transform, and I'm going to take the coefficient and transform the MA, but again we have to do this MA dot reshape -1 comma 64 times 64. Okay, so let's see coef. So this is the data, and this is 1,000 components. You can see that some numbers are pretty big. These are pretty big numbers in the hundreds, and you get some negative exponents way at the end. So this will be kind of small. So let's see what happens if we add these components back. So I'm going to say A is equal to numpy zeros with shape, and I'll make it as 64 by 64. Shape equals to 64 by 64. So just make zeros out of A, and then I'm going to do for C in coef. Did I make it coefs or coef? Just coef. Okay, so coef 0, so it goes through all the numbers, and then I add to A. A is equal to A plus the PCA components. I have to enumerate, sorry. I comma C, enumerate. Okay, PCA dot components I, and then times the coefficient, which is C. Okay, so I do that, and if I add all the, okay, let's not add all of the coefficients. Let's just use the first 100. Okay. Now let's show. No. Oh, sorry. I need to reshape this. Dot reshape 64 by 64. Okay, and then plt dot show A. Does this look like Muhammad Ali? No. Okay. Well, here's the original plt dot faces 9355. Now plt dot show faces. This is the original picture. This is 100 features. Okay, let's go to 500 and see if it's better. Okay, so I have to make it 0 again. How about that?
It's getting better.
It's getting better. 500 features. It reconstructs the original image pretty well, right? And then if I do all of them, 1,000. So it's pretty good, right? So, and then you can think about how much data memory you save. See, original one was 4,096 pixels, whereas this is 1,000 information. So only with 1/4 of the information, you've reconstructed the image like this. Now, it's also important to do this in a support vector classifier. So it's something nice to try if you want to do it on your project, because if you reduce the dimension, it allows you to avoid something called the curse of dimensionality. So when you have a lot of feature sets, then these values that some noise values in the features that are not important makes the distance between two data points too large than they actually are. So it's much better to project your data set to using the PCA to a lower dimension and then do the support vector classifier. Right, that's all for today.